Hello, this is Mr. Huber. In this lesson, we're going to look at solving systems of equations algebraically. We've seen how to solve systems by graphing, and that method can be difficult if you don't have a graphing calculator or some other device to help you with the graphing. Being very exact and precise in drawing graphs is not that easy to do, and so there's some other methods we want to use because graphing isn't always ideal. One of the methods we're going to be able to learn is substitution. This is where we're going to figure out the value for one of the variables and plug it in to solve for the other one. So you can see here from the steps that we're going to solve one of the equations for one of the variables. So we're going to get one of the equations solved for x or for y. It doesn't matter which one. Okay? Then we're going to substitute that value for x or y into the other equation in our system, and we're going to get a value for x or y and then substitute that value in to find the other variable. So we'll see how these steps can work in a system of equations here that we can solve. We've got the system y equals 3x plus 2 and x plus 2y equals 11. So this first system is actually already solved for y. It's written as a y equals 3x plus 2. So we can take what y is equal to and substitute it in here for y into the other equation. That will give us the second equation of x plus 2 times 3x plus 2 equals 11. So we've replaced the y with 3x plus 2. Again, we've taken 3x plus 2 and we've substituted in here for y because that's what y is equal to. And now I can solve this system of equations by distributing the 2 into the parentheses. I'll get x plus 6x plus 4 equals 11. And then I can add the x and 6x. I get 7x plus 4 equals 11. That gives me 7x equals 7. And I divide both sides by 7. I'll get x equals 1. Now that I know what x is equal to, I can take that value for x and I can plug it back up in here to find out what y is equal to. So I'm going to take this equation here, and I'm going to write it out as y equals 3 times, we know x is equal to 1 because we just solved for it, we plug that in for x, and now we can get y equals 3 plus 2, and we get y equals 5. So the solution for our system is an ordered pair 1, 5. Remember, like when we graphed these, that would be the point where they would intersect. If we graphed these two equations, they would intersect at the point 1, 5. This is the solution for the system. Remember, that means it should be a solution for both equations. So we could plug in a 1 for x and a 5 for y into both these equations and make sure it works. That's how we can check our solution. Okay? If we put an x, 1 in here for x, and a 5 in here for y, we'd have 1 plus 2 times 5 is 10. That'd be 1 plus 10 is 11 equals 11. We'd see that it works, and we could do the same up here. We plug in a 5 for y, we get 5. Equals 3 times 1 for x, so that's 3 plus 2 is 5 equals 5. So we would see that this is a solution for both equations. It's the solution for the system of equations we see there. Here's another opportunity to solve by substitution. Right? Neither of these equations are already solved for x or y, but we could take this second equation and we could get the x by itself by just subtracting 3y onto both sides. So let's do that. We're going to subtract 3y on both sides. And we're going to get x equals negative 3y minus 7. Now we could take that and we could plug it in up here for x. Okay? So we're going to take this equation. We're going to have negative 2y plus 4 times negative 3y minus 7 equals 0, right? We've taken this negative 3y minus 7, we've put it in here for x, right? So instead of 4x, we have 4 times negative 3y minus 7. And now we can solve this system by distributing the 4 into parentheses. We have negative 2y minus 12y minus 28 equals 0. That's negative 14y. We add 28 to both sides, equals 28. And if we divide both sides by negative 14, we get y equals negative 2. Now I could take that and I could plug it into either of my two equations that I had at the beginning. I can take that and plug it in here or into this equation. It does not matter which equation we use. I'm going to take the second equation, okay? And I'm going to substitute that value back in there. So I'm going to have 3 times negative 2 plus x equals negative 7. That's negative 6 plus x equals negative 7. Over here, that's adding 6 to both sides, x equals negative 1. So negative 1 comma negative 2 as an ordered pair, x comma y, that would be the solution for that system of equations. Again, we could check that, plug those x and y values in, negative 1 for x, negative 2 for y, and make sure that it actually works in both equations. That's how we could check the solution. It's not always easy to get one of the variables solved for, x or y. In the system we see here, if we wanted to solve, let's say, this first equation for x, I could subtract the 3y on both sides, and I'd be left with 2x equals negative 3y plus 11. And then if I divide by 2 on both sides, to get x by itself, I'd have x equals negative 3 over 2y plus 11 over 2. And then I'd have to take that and plug it into this other equation for x. I'm going to have the fractions to deal with that are going to be a bit of a pain. That's not really the easiest way to go. So we're going to learn another method for how to deal with systems of equations like these where it might not be easy to solve for x or y and substitute in. Okay, so there's going to be another method that we can use. Before we show that first, just a quick reminder about how important bacon is, right? Never enough in the package. It's always gone before everyone gets as much as they want. But hey, we'll take what we can get. Try not to be too picky about that. Now let's learn about the elimination method for solving systems of equations. And this is going to be a method where we're going to add or subtract two equations together to eliminate, to cancel out one of the variables. Then we'll have one variable left over that we can solve for, and we can substitute that back into the system to solve for the other variable. Okay, so we're going to see that system I had up there just a moment ago where we saw this could be difficult to solve for x or y and go from there. If we add these two equations together, we're going to add this whole second equation to the first one. 2x right here plus negative 2x. When I add those together, they're going to cancel out. And then I add 3 plus 5 is 8y equals 11 plus 13 is 24. And so by adding those and canceling out the x, we have a relatively straightforward equation we can solve for y. By dividing both sides by 8, we get y equals 3. And now I could take that y equals 3, and I could plug it into one of these two equations for y. I'm going to take the first equation. I'm going to plug y into that equation. So if I do that, bring that over here, I'm going to have 2x plus 3 times 3 equals 11. That's 2x plus 9 equals 11, and 2x equals 2. Dividing both sides by 2, I get x equals 1. So my solution for the system is 1, 3. Again, we could see where before, if I had solved that for x or y and had those fractions and then substituted in the fractions, there would have been some challenging work to follow through on. It would work if we did it, but this method will help simplify things quite a bit if we can eliminate one of the two variables. Sometimes you have to subtract the two equations. So you got to look at the two equations and see what am I being given. In this case, if I added these two equations, okay, if I do 5x plus 7x, I get 12x, plus 6y plus 6y is 12y equals 0. I'm not going to get very far because I didn't eliminate either of my two variables. So I don't want to use that method. I need to be able to eliminate, okay, one of the two variables. So in this case, I can do that by subtracting the two equations. If I subtract these two equations, and the parentheses around here are important to make sure we know we're subtracting the 7x, subtracting the 6y, subtracting the negative 8. Make sure you're subtracting the entire equation. So we're going to have 5x minus 7x. So we start there, 5x minus 7x is negative 2x. 6y minus 6y cancels, and 8 minus negative 8 is 16. We're subtracting a negative. Divide both sides by negative 2, and we get x equals negative 8. And now I can take that negative 8 for x, and I can plug it into either one of these two equations. I'll take the first equation again. It really doesn't matter. You can pick either one you want. So I take this equation. I mostly picked this one because it didn't have a negative 8 in it. If I can avoid negative numbers, sometimes that might be useful. And so I plug in my negative 8, I get negative 40 plus 6y equals 8. That's 6y equals 48. When I add the 40 to both sides, I'm going to get y equals 8. So I've got my solution of negative 8, comma 8. Okay? You can use elimination by adding or subtracting the two equations. Again, you've got to look at the two equations you're working with and see which one will eliminate one of the two variables. There's one other factor to this that can add in another layer. Sometimes neither of the two variables will eliminate through addition or subtraction. If we add or subtract these, the x's aren't going to cancel and the y's aren't going to cancel because we don't have the same coefficient in front of either of them. We've got a 6 and a 2. If I add those, I get 8. I subtract, I get 4. If I add these, I get 8. I subtract, I get 2. They're not going to cancel out either way. But you can multiply entire equations by whatever you want. So in this case, I'm going to recognize that if I multiply this by negative 3, I'm going to get negative 3 times 2 is negative 6x. So my first equation isn't going to change. 6x plus 5y equals 19. My second equation is going to be negative 6x, because I'm going to distribute the negative 3 to the entire equation, minus 9y equals negative 15. And now I can add these two equations together. Okay? When I add these two equations together, those cancel out. 5 plus negative 9 is negative 4y. And then 19 plus negative 15 is 4. Divide both sides by negative 4 and I get y equals negative 1. So you can see after I multiplied one of the two equations, that allowed me to use elimination. And now I can take that negative 1 for y and I could plug it into either of my two equations. I'm going to take the second one here. So if I take my second equation and I'm going to take 2x plus 3 times y is negative 1 equals 5. That's 2x minus 3 equals 5. 2x equals 8 when I add 3 to both sides. I'm going to get x equals 4. So my solution is 4 for x, negative 1 for y, 4 comma negative 1. Right? So we've seen a couple methods here we can use for solving systems of equations. Substitution, if you can know what x or y are equal to get the x or y by itself. Again, generally, you want to do that if there's no coefficient in front of an x or y. If this 2x wasn't here, it was just an x, I could get the x by itself pretty simply by subtracting 3y. Okay? But if you've got coefficients in front of the x's and y's, you're probably going to use elimination. And if there's not elimination set up the way they're written, multiply either one of the two equations by anything you want and get it to where you could then cancel out one of the two variables. Okay? Again, I don't want to multiply this by negative 8 because that's not going to get any of this to be able to set up to cancel out. So you do have to pay a little attention to what you're multiplying by and kind of think that through a little at the beginning. Let's see where we can apply a system of equations to a situation. Okay, here we have a cafe that sells a regular cup of coffee for $1 and a large cup for $1.50. Melissa and her friends buy 5 cups of coffee and spend a total of $6. So we're going to write a system of equations, 2 equations. One's going to be based on the number of cups of coffee, and one's going to be on the amount of money spent on the coffee. So we're going to say x equals regular and y equals large cups of coffee. So if we add the number of cups of coffee they bought together, they bought a total of 5 cups of coffee. If we talk about the amount of money they're spending, so $1 for every regular cup plus $1.50 for every large cup, it's going to equal $6. Right? So we saw that if we write our system of equations, we've got one based on the amount of money they spent, $6, $1 for every regular, $1.50 for every large. Okay? And then we've got the number of cups. They buy 5 cups of coffee, so the regular cups plus large cups. So one's the number of cups of coffee, one's the amount of money spent on the cups of coffee. Now if I want to solve this, I could eliminate or substitution. I could solve this for x or y, I could solve down here for x pretty easily, or I could use elimination. It's kind of up to you. I'm going to show with elimination. Okay? If I subtract this equation, x minus x cancels out. Now I have a 1 in front of this y. 1 minus 1.5 is negative 0.5y equals 5 minus 6 is negative 1. If I divide both sides by negative 0.5, okay, that's y equals 2. So I have y equals 2. Remember, y is the large cups of coffee. So they bought 2 large cups of coffee. The question asks me, find the number of small cups of coffee. So I can take the 2, or regular cups, I can take the 2 and I can plug it back in here for y, because I know that when I add them together, I should get 5. So I'm going to have x plus 2 equals 5, which means x is 3 regular, or small, cups of coffee. Okay. So we can write a system of equations. We've seen these before based on the different situations we're given, and now how we solve them, again, depends on what the equations look like and what method you think might work best.